Hi and welcome to Bro Abhiyantriks. In today's video, we are going to talk about problems on deflection of composite materials, and also we are going to talk about uh, statically indeterminate problems. Right. So anyway, we'll start with the first problem here. Rigid bar ABC. Okay, we have three bars supported by three wires. Okay, we have rigid bar here that is been supported by three rope or three wires of same material and same diameter as shown in the figure. Okay, so we have same diameter, same cross sectional area and same material, so the E will also be same. Okay, calculate the forces in the wire due to applied load P if the bar ABC remains horizontal after the load has been applied. Right, so this is important. They are specifically saying that the bar ABC remains horizontal, means that after the extension, so ABC is going to be somewhere here, meaning that the deflection in all the three ropes will be same. Right, so keeping this in mind, first let us apply the static equilibrium. In the static equilibrium, what does that say? The load applied will be equal to the reaction loads. Right, so meaning that the force P, the load P that has been applied, will be equally distributed among all the three wires. Right, so meaning that if the reaction force here is, let's say, in a smaller rope it is, let's say, P1, and in the another smaller rope again it's, let's say, since it is of same length, again it will be P1, and in this guy we are going to have P2. So meaning that we are going to have P1 plus P2 plus P1 will be equal to P, meaning that 2P1 plus P2 will be equal to the applied load. Let me call this as equation 1, and now let me apply the other thing, which is delta 1 is equal to delta 2. Right, let me apply the formula for delta. So that is nothing but PL by AE. So here for 1, meaning smaller rope, so the load will be P1 into L, so this is L whole divided by A and E, so will be equal to for the rope 2, so this guy, meaning P2 into L, the distance is 2L divided by AE. So here L and AE and AE will be cancelled, L and L is cancelled, so P1 is equal to 2P2. So I'll call this as equation 2. I'll apply equation 2 in equation 1. So I'll be having 2 into 2P2 plus P2 will be equal to P. So 5P2 is equal to P. It means that P2 is equal to P over 5. So again I'll apply this back in equation 1. So I'm going to get 2P1 plus P2 is equal to P. So I have the P2 value. So 2P1 is equal to P minus P by 5. So which is nothing but 4P by 5. So 2 will be cancelled here. So totally P1 will be equal to 2P by 5. Right. So let me move on to the next question. So here a composite bar of cross section area 2B into 2B, okay, is constructed of two different metals having the moduli of elasticity E1 and E2. The two parts of the bar have the same cross-sectional dimensions. Okay, so cross-sectional area is same. We have different metals. Okay, so the bar is compressed by forces P acting through the rigid end plates. The line of action of the loads has an eccentricity E of such magnitude that each part of the bar is stressed uniformly in compression. Okay, so now they are talking about a composite bar of two metals. So let me just draw a schematic for that. Since they have said that it has same cross-sectional area, I'll be drawing this as this. Okay, the dimensions here would be 2b cross 2b, so meaning that, so this entire bar length would be 2b, right? So I don't want this. I'll individually say that this length is b and this length is also b, right? Now this will be held together by a rigid end plate. This end plates are able to move, and the load is applied for an eccentricity. Okay, so this length is E, and sorry, this length is E and this load is what, P. Okay, so with this, and the length is L. I'll just call this as material 1 and I'll call this as material 2. And now with this information, let me start solving the problem for the fluid body diagram. So I'll have a end plate here and I'll have a material 1 and material 2 here somewhere here, right? So I'll be having an eccentric P here, and this would be E, and the reaction given by A or the material 1 will be somewhere here, and reaction given by material 2 will be also, this will be P2 and this will be P1, right? So the distance between these two will be again be equal to B, because this will be the center of the first element, this will be the center of the second element, and vice versa, right? So now I'll apply the static equilibrium. So in static equilibrium, I'll be getting as P1 plus P2 will be equal to P, and I'll call this as equation 1. Okay, now since these two plates are held by a rigid plate, the deflection in both of these materials will be same, meaning that delta 1 will be equal to delta 2. Straightforward, I'll be applying the formula again. P1 into L divided by A into E1 is equal to P2 L divided by A into E2, and again AL will be cancelled, so the remaining is, I'll write in terms of P1 is given by E1 by E2 into P2. Now I'll apply this in equation number 1. I'll have equation 1 will become, I'll take P2 as common now, so P2 into E1 by E2 plus 1 is equal to P. Okay, now P2 is equal to E2 into P divided by E1 plus E2. Okay, now for P1 is again equal to P minus P2, that is nothing but P minus E2 P divided by E1 plus E2, now which is nothing but P E1 divided by E1 plus E2. Okay, so now the second part of the question is determine the eccentricity E of the loads. So okay, for E, what do we have to do? Fairly simple thing, we'll just take a moment about the line of action of P. So on this particular point, let me call this as, let's say, A. Upon A, I'll take the moment acting, right? Upon taking moment on A, so I'll be having the minus P into B by 2 plus E, right? So I'll have P here, this length is B by 2 and plus E is B, right? Plus P2 into B will be equal to 0. Now B by 2 plus E is equal to P2B by P. Now E is equal to P2B by P minus B by 2, so which is nothing but 2 P2B minus BP divided by 2P. Now if I simplify this again, I'll substitute the value of P2 for this equation, so I'll be getting it, I'll be skipping all the simplification steps. Finally the answer that I'll be getting is B by 2 into E2 minus E1 divided by E1 plus E2. Right, so what do we have to do? We simply have to put P2, value of P2 in this particular equation and solve. Okay, so let me move on to the next question. Now a circular bar ABC is equal to 200 GPa has a cross-sectional area A1 from A to B. From A to B, the cross-sectional area is this much. Alright, the cross-sectional area A2 from B to C, from B to C, so this guy. we have the cross-sectional area as A2. Okay, and the bar is supposedly rigid at end A, so meaning we have a rigid support at end A, meaning that A is not be able to move forward. Okay, and is subjected to a load P equal to 40 kilonewton at C. So this C we have 40 kilonewton. Okay, and a circular steel collar of BD having cross-sectional area A3. So again, this guy BD, the collar is here. This is the area is A3. Okay, supports the bar at B. So again, this is B, and again D is a rigid end. The collar fits snugly at B and D where there is no load. Determine the elongation delta AC. So we'll need to calculate the total elongation of the bar. Okay, assuming L1 is equal to, I'll be writing down all the data that has been given. L1 is equal to 2L3, that is equal to, so I'll individually write this. L1 is equal to 250 mm, L3 is equal to 125 mm, and L2 is equal to 225 mm, and A1 is equal to 960 mm square, A3 is equal to 320 mm square, and A2 is equal to 200 mm square. Okay, now here first let me apply the static equilibrium. If we apply the static equilibrium, all the reactions will be equal. So the reactions here that we will be getting is P1 at support A, and at support D we will be having another reaction. So meaning that P1 plus P2 is equal to P. Note that these two are one and the same. So this is a circular collar here. So this will be entirely circular. We are not supposed to take P2 plus P2. That doesn't make any sense. This is an entire single body here. At AB, this is a one single body. So again, P1 plus P2 is equal to P. Now again, I'll call this as equation 1. Now AB and BD are fixed. So meaning that A is at end A is it is fixed, at end D is also fixed, meaning that the entire AD, the elongation will be same. Meaning whatever the elongation that is happening in AB will be equal to the compression that is happening in BD, right? So meaning that delta AB plus delta BD will be equal to 0. So, and again I'll call this as equation 2. So here what is happening? I'll individually write the equations now. Delta AB is equal to P1 L1, right? So divided by A1 into E, right? So this is elongation. I'll have it as positive. And for delta BD I'll be having, so this will be in compression, minus P2, the length is L3, divided by the area is A3 into E. Now if I substitute it back, P1 L1 by A1 E is equal to P2 L3 divided by A3 E. E will be cancelled. If I substitute the rest, I'll be able to calculate P1. Right, so let me just write down the couple of steps here. Let me substitute the value for P2 from the equation 1. So I'll be having P minus P1 into L3 divided by A3. Now if I take all the P1 to the LHS, I'll be having P1 into L1 by A1 plus L3 by A3, that will be equal to L3 by A3 into P. And now if I simplify for P1, I'll be getting as P1 will be equal to A1 L3P divided by A3 L1 plus A1 L3. Now if I substitute all the values here, I know the value of A1, I know the value of L3, A3 is also known, L1 is also known. So if I substitute all the values, I'll be having, let me just write one more step to just for the substitution purpose, 960 into 125 into 40 into 10 to the power of 3 whole divided by 320 into 250 plus 960 into 125. So if I simplify this, the answer will be, I'll be getting as 24 kilonewton. Okay, so now for P2 it is nothing but 40 minus 24, which is nothing but 16 kilonewton. Now for elongation in BC, so elongation in BC is again nothing but the load acting on the member BC. So here the load acting on this particular member is 40 kilonewton. So it is nothing but P, the length here is L2 divided by A2 into E. So which is nothing but 40 into 10 to the power of 3 into L2 is nothing but 225 whole divided by A2 is 200 into E, it is given as 2 into 10 to the power of 5. So upon simplifying, the answer that I'll be getting is 0.225 mm. Now we are supposed to calculate the total elongation from A to C, right? So whatever that is compressed, that the body is getting compressed in BD will be equal to the elongation in AB, right? So I'll calculate the compression in BD now. So delta BD will be equal to minus P2L3 divided by A3E, right? So I'll be calculating for this steel collar now, right? So upon substitution, I'll be having minus 16 into 10 to the power of 3 into 125 divided by 320 into 2 into 10 to the power of 5. So which is nothing but minus 0.03125 mm. Now delta AB is equal to minus delta BD, so which is nothing but 0.03125 mm. Now upon applying the principle of superpositions, delta AC is nothing but delta AB plus delta BC, so which is nothing but 0.225 plus 0.03125, so which is nothing but 0.256 mm. Right, so let me move to the next question. So here we have two prismatic bars are rigidly fastened together and support a vertical load of 40 kilonewton as shown in the figure. The upper bar of steel having a unit weight of 960 kilonewton per meter cube. So I'll just simply take down the values as it goes along. So the load, I'll make it as P, it is equal to 40 kilonewton. Okay, and for steel I'll use the subscript S, and for brass I'll be using the subscript B. Now they are talking about the upper bar of steel. So okay, have the unit weight is, let's say, gamma S is equal to 760 kilonewton per meter cube. Okay, the length LS is equal to 10 meter, and cross sectional area AS is given as 80.7 centimeter square. If I convert that to meter, I'll be getting as 80.7 into 10 to the power of minus 4 meter square. The lower bar of brass having a unit weight. So now let me go to the brass. Gamma B is given as 800 kilonewton per meter cube. Okay, the length LB is given as 6 meter, and the cross sectional area AB is given as 64.5 centimeter square, so which is nothing but 64.5 into 10 to the power of minus 4 meter square. And also ES is given as 207 into 10 to the power of 9 Newton per meter square, and EB is given as 90 into 10 to the power of 9 Newton per meter square. Now determine the free extension of free end due to self weight only. First of all, we'll have to neglect this P, and then we'll have to calculate the free extension, and then we'll have to calculate maximum stress in each material considering the load. Okay, so now first, without only free extension. Now before getting into this, let me write down some formulas for this. Free extension of a particular prismatic bar. So what is that given by? So the delta of a prismatic bar is given by the weight of the bar into L divided by 2 into AE, right? So what is this W? The weight is given by the unit weight into area into the length. So the gamma will be given in terms of Newton per meter cube. Right, so using all of these formula, let us calculate the various elements. So now, firstly, without due extension due to self weight. Okay, for this, first I'll be considering delta. What is this for brass? BC, delta BC, right? So I'll be calling this as delta 1, BC weight. Okay, so now delta 1 is given as WB into the length of brass LB divided by cross-sectional area of brass into modulus of elasticity of brass into 2. Now upon substitution, I'll be having as the WB is again given by gamma B into AB into LB divided by 2AB into EB. So AB is cancelled, so LB into LB will be LB square. So now if I substitute all the different things, I'll be having as 800 into 10 to the power of 3 into 6 square whole divided by 2 into 90 into 10 to the power of 9. So upon substitution, upon simplification, I'll be getting as 160 into 10 to the power of minus 6 meter. Now if I want to convert this into millimeters, I'll be getting it as 0.16 mm. Okay, now I'll consider the AB, the steel bar, due to its weight. Now I'll call it as delta 2, which is nothing but WS into LS divided by 2 into AS into ES. Again, upon simplification, I'll be having substituting the W in terms of gamma. Let me just write it as gamma is nothing but 760 into 10 to the power of 3 into AS will be cancelled in the denominator and numerator, and again LS will be squared, which is nothing but, so here LS is 10 meter, so 10 square divided by 2 into 207 into 10 to the power of 9. Okay, so which is nothing but 1.835 into 10 to the power of minus 2 meter. Now which is nothing but 0.1835 m. Now again extension of AB due to weight of BC. Now we'll also have to consider this. So delta 3, I'll call this as delta 3, is equal to WB into length LS, length of steel, divided by the area of steel AS into ES. Now this is not the self weight of the steel, this is the weight of brass which is acting upon the steel, right? So again, that is why in denominator we are not using the 2. Now here the weight of WB. So here WB will be equal to, let me just substitute the values here, gamma B into AB into LB into LS divided by AS into ES, right? So which is nothing but, if I substitute 800 into 10 to the power of 3 into 64.5 into 10 to the power of minus 4 into 6 into 10, right, whole divided by 80.7 into 10 to the power of minus 4 into 207 into 10 to the power of 9. So if I simplify this, I'll be getting as 0.1853 mm as the answer. Right, so the total extension will be equal to delta 1 plus delta 2 plus delta 3, the principle of superposition. So the total answer will be equal to 0.5286 mm. Right, so now we'll have to calculate the maximum stress. So the maximum stress for this particular element. So for brass, the maximum stress will be in this intersection. Right, for steel, the maximum stress will be in this particular point. Right, so if I want to calculate that, let me first calculate for brass. I'll be calling this as sigma B max will be equal to the load, that is P, plus the self weight WB divided by the cross sectional area AB. So which is nothing but P is nothing but 40 in plus this is 800 into 64.5 into 10 to the power of minus 4. Remember, W is equal to gamma A into L into the length 6. So whole divided by 64.50 into 10 to the power of minus 4. So if I want to convert this into mm, so I'll be so this is in meter square. If I want to convert that into mm square, I'll have to multiply with 10 to the power of 6. So I'll be getting as 6450 as the answer here. So now if I upon simplification, I'll be getting as 11 Newton per mm square. Also, again into 10 to the power of minus 3 is also there in the numerator. So this is in kilonewton, right? So for steel now, max will be equal to the applied load P plus the weight of brass plus the weight of steel divided by the cross sectional area of steel. So which is nothing but upon simplification, WB will be equal to 30.96 kilonewton and WS will be equal to 61.33 kilonewton. Right, so applying this particular formula, right, so the total load will be 132.92 into 10 to the power of 3 divided by 80.70 centimeter square. If I want to convert that into mm square, I'll be getting as 8070. So upon simplification, I'll be getting as 16.4 Newton per mm square as the maximum stress in the steel bar. Right, so let me move on to the next problem, the last problem in this video. For the composite bar of two metals as shown in the figure below, the ratio ES by EC is equal to 2. Right, so for composite bar as shown. Okay, now this is a particular problem on statically indeterminate equation. So here these two ends of these two particular bars is rigid, meaning that these two will not be able to move. So meaning that the total delta of this entire AC will be equal to 0, right? So which is nothing but the total elongation of this entire body will be equal to the elongation in first of all, let me just write the static equilibrium equation. In the static equilibrium equation, so P will be equal to P plus RA will be equal to RC, right? So P will be equal to RC minus RA. I'll call this as equation number 1. Now if the end C and end A are fixed, the total elongation will be 0. So the total elongation delta AC will be equal to 0. I can split up the delta AC as delta AB plus delta BC will be equal to 0. Right, so the point of application of load is at B in the downward direction, meaning that AB is getting compressed and BC is getting elongated. Right, so now with this particular knowledge, I'll go with the free body diagrams for this copper. For copper, again we'll have tension. The forces tension for tensile force will be the support reaction, the reactive forces RC. Now I'll call this as equation number 2. Now equation number 2 will be given as, now applying and again the free body diagram for the steel. So here again we'll have a tensile force upon this. What is the tensile force? Which is nothing but RC minus P here, right? So again here also we'll have RC minus P, so which is nothing but RA actually, right? So this is copper and this is for steel. Now upon this we can write down the individual delta equations for copper as well as for steel. So which is nothing but, for AB for copper, so we'll have the load acting, that is RC, so it is tensile. I'll have plus into the length that is given as 2L by 3, that is 2L by 3 divided by the area into the element modulus of elasticity EC, plus this is also in tension, plus RC minus P, right? This is the load that is acting, RC minus P, into the length is L by 3 whole divided by A into S, that is equal to 0. Now I can cancel off L by 3 and L by 3 here. I can cancel A and A also. Now if I send this particular unit to the RHS, I'll be getting as 2RC divided by EC will be equal to P minus RC divided by ES. Now upon simplification, I can find out the value for RC in terms of P. So which is nothing but, I'll skip the simplification process. RC will be equal to P by 5, right? So this is in tension, right? So note that this kind of problems wherein we have a particular material, the ends of the material are restricted to move, right? So to solve these kind of problem, only the static equations is not sufficient. So what do we have to do? We'll have to also use the delta equations. So these kind of problems are called static or statically indeterminate structure. Alright, so hopefully this video has been helpful for you. Please like, share and subscribe. Thank you for watching. See you in the next video.